Assalamualaikum and a very good day to all. So I am Ummikalsom Abidin from School of Mechanical Engineering, Faculty of Engineering, Universiti Teknologi Malaysia for the second International Conference on Applied Thermo-fluid and Computational Fluid Mechanics 2022. I would like to present on our research about the characterization of fluid flow through a porous media. Okay, so for the outline for the presentation, so I will go to the introduction, a little bit on the background and also literature. And then I will go on the objective why you want to do the research, okay, and the methodology that have been conducted, the result discussion, and also the conclusion. Okay, so our study related to the paper-based microfluidics. So before we go in detail about what is actually a microfluidic paper-based, so what is actually a microfluidics? So microfluidic is actually a device that can be able to manipulate a very small fluid volume. Okay, I mean not manipulate in terms of the process. Okay, can process. So it will be in terms of the microliter to the picoliter range. Okay, and it can have a dimension, one of its dimension in the micrometer length scale. Okay, so it's used for like in a micro channel. Okay, and also another important microfluidic is related to the paper-based analytical devices. So the paper-based analytical devices, just like our COVID-19 RTK test kit. Okay, and also like the pregnancy test kit that is normally previously been widely used. Okay, so it has a paper where when we put our sample, we can see how the fluid flow, and then because the paper already been loaded with a certain chemical that have the reaction with the biological fluid, so it can indicate or it can give you the diagnosis whether you have whether it's negative or positive. So what is actually the advantages of this paper-based microfluidic is low volume because you can just like have a very two droplets of your saliva, and then it's also use a very small reagent, okay, that the chemical that been embedded on the paper, because the reagent is normally very costly. Okay, so if you have a low sample volume of reagent, so you can save a lot, and that's why you can have a very low cost test kit, right? So it based on the capillary flow, and then it's a portable, okay, fast reaction, okay, same like our RTK test kit for the COVID-19. It be able also to use to do the multi-analysis. Maybe in the future, maybe some of the research they'll be able to indicate like in terms of the level, okay, or in terms of the severity, okay. So there is a future, the current also the future study that been done. If it's fabricated using the flexible plastic, so it will be very flexible. So just I mentioned, in terms of the main application is related to health diagnostic. Okay, but it's also been used in environmental monitoring where you can food quality. Okay, where you can know the chemicals that in the, for example, like in the water. Okay, or in the food, and then in the drinks. Okay, and then it can know like the acidity, right? Okay, other than that, also be used in drug analysis and also the cells AC in terms of the cell biological studies. Okay, so what is actually a porous material? Okay, filter paper, a paper, like also our clothes is actually a porous material. So normally it has a multiple hole through and made of interwoven and cross-linked fiber. So it can be like well-defined or it can be just like a random configuration of these cross-linked fibers. Okay, it's primarily being used in the separation of the solid and the liquid. Okay, just like our filter in our home. So we don't want unwanted solid content, or so we need to do the filtration. Okay, so it just have the same function. So Wattman is actually one of the famous brand, okay, manufacturer of the filter paper. What are actually the factors, okay, related to the characterization of this fluid flow? So it will be related to the permeability. Okay, permeability is the ability to transfer the fluid, is how it can be absorbed. Okay, how easily the fluid can flow through the porous media. So it means more permeability is more easier to flow. Okay, or this is called as a wicking. Okay, the absorbing behavior is called a wicking. Okay, porosity measure the vacuum of the void spaces. Okay, related if you have like your paper and you see it from the using the microscope or the scanning electron microscope, you can see that it's actually it has a void or the vacuum spaces. Okay, that is what we want to do in our study to find this with the image processing. Okay, of the study, okay, the literature review or the past study related to the filter paper, it will be closely related to the intended application. Okay, for example, here because maybe the application they need to use the filter in a very high compression, so the researcher make a variation of the pressure, and then from the effect they get this SEM images, so can see that the thickness, okay, and the micropore images. Okay, so they can actually know how will be the effect of the porosity and the permeability with the paper under a press condition. Okay, so you can see that it has a very high compression, thickness is also decreasing, so it will have a less permeability and less pore size actually. Um, so in terms of other research also, they make kind of model, the electrical circuit analogy model, okay, and compare it with the theoretical Lucas-Washburn equation and with the experiment. So the electrical circuit analogy, I think, is very common in fluid mechanics, okay. It's been used previously like in a tube, in a microchannel, okay, in a pipe, okay. You just want to know on the model, okay, where they relate between the flow rate with the current, fluid resistor with the resistance of the electrical circuit, okay, then you can also predict this pressure difference. So this is when the advantage of you have the model, so you don't have to do a lot of experiment, but you can also have a very good prediction of whatever parameter that you want to study. Okay, another very interesting is related to the I-simple. I-simple is the infusion self-power imaging microfluidic pump by liquid encapsulation. This is a passive micro pump because it don't have the external power. Okay, it don't need any external power. So it's actually the porous media is placed in a sandwich configuration. Okay, so it's been secure, okay, in between two plastics, okay, and then they make a pattern there where they put this filter paper. So when in here, the blue color one is a working liquid. So and the red color one is we call a sample liquid, the biological sample liquid that we want to process or to analyze. Okay, when we put is the working liquid here, when we press it, so the liquid will go to this filter paper. Okay, and then it been absorbed, and whatever air inside the filter paper will push it because it's a confined environment. It will push, okay, or a confined or the closed environment, so it will push the air inside the filter paper, okay, will push the sample liquid to flow. Okay, so this is actually a micro pumping effect. So for this, they'll also actually do a lot of experiment on a different filter paper and how it affect in terms of this sample liquid flow at a different section of the channel. Okay, so like I said, whatever you want to do in terms of the past research, they did it for the whatever porous media that they use and its application. So some of the data are still limited. Okay, we don't know for the porous media that we use and for our application, what will be the relationship, okay, that we can relate with for our study. So it's very important to conduct this research based on our specification and also the depend on the porous media specification and the application that we want to apply it. Okay, so the objective is related to the characterization. So we we need to characterize our porous media, and then we need to use to characterize also the wicking or the water flow through this porous media under with different area and also with different environment. So this is the filter paper that we use. So the fast flow, so it has a high the greatest particle retention related to the size of the voids, that is the greater void. Okay, and then the slow flow is related to the smallest solid particle that it can filter and is related to the smallest void size available in the filter paper. So this is from the Wattman filter paper. So from the image, from the SEM images, we make the analysis using this image J. Okay, we enhance the image and everything. And then we get the porosity value, the void that we can count, the area, and then we relate with the total area of the filter paper so we can know the porosity. In terms of the wicking behavior, so we make a different size. Okay, this is vertical condition. The A1, A2 is double from A1, and the A1 and diamond is actually the same area and is same type, is same volume. So and then we want to know on the effect of this shape. Okay, this is how the experiment being conducted. So we need to control our temperature and also the humidity for our location. So this is how we can see, we can put the scale, okay, and then we can do the time taken, okay. So this is from the SEM images and from the image J. Okay, so we can get the porosity around about 70%, okay, for 40, 41 and about 62% for 42. So 70% is actually the same approximation by the Del Doso, okay, previously. So it's a good value that we get. So in of the result and discussion, when we see here, so it's actually all these will be related back to the specification of the paper. We can see that for the 42, because it is a fast flow, sorry, for the 40, yeah, 42 is the slow flow, okay, the slow flow. So slow flow, so of course it will take more time, okay, because it has a very small void, okay, so it has a greater time to taken for the fluid to flow. But for the 41, is a fast flow, is just a very short time duration. Okay, in terms of the, and we can see here for the A2 also, only if it's only double, okay, from the A1, but it will take more time because, you know, at a vertical condition, it has also the gravitational effect and also the effect of the evaporation. So it is much, much greater, the time taken, even though the area is just double, okay. Okay, and then we look at for a different shape. Okay, so for the same area, and if same grade is same volume, because the thickness is the same, so we can see with the diamond is slightly more, the time taken for the fluid absorption is slightly more because it's maybe because of the divergent, and then it will take a little bit greater time for the fluid to absorb. Okay, and then for the confined environment where we have the sandwich configuration, same like the Daldoso, so it's greater time taken for the fluid to flow because of the effect of the lamination, okay, the adhesive on the laminating that is can be melted during the lamination and cause the resistance. Okay, in terms of the flow rate, so of course with the fast flow, it will have a higher flow rate. And the opposite is true where it has a very lowest pressure difference because it has a highest flow rate. Okay, so it's still depending on the specification of the porous media. Okay, in terms of the Lucas-Washburn equation, so we can see that it's follow a Lucas-Washburn equation where this is actually the quadratic relationship between the height and also the time taken. So this is also true for all of the filter paper 40, 41, and 42. Okay, where we can see only for the 42, it will easily, okay, the time taken is for the same scale, okay, so it will take a shorter time, okay, for this 41, okay, the behavior of 41 because of the specification. Okay, the fastest, okay, the fast flow category. Okay, I think that is our conclusion. We'll be able to get the porosity and be able to know the behavior, especially on the parameter of interest, because we want to study on the micropump that is being fabricated in the confined environment. And it will actually very important for our future study where we can make a prediction, a good prediction or analysis related to the micropump application that we are going to conduct in details later. Thank you.